Assalamualaikum and hi to Dr. Izni Ibrahim. Today we from Group 2 are going to present our project which is water delivery system of vegetable farms. Here are the group members of Group 2. We have Nur Ainun Baisyirah, we have Harith Hadif, and we also have Nurul Afifah. So, for the background, from what we know, the project's goal is to construct a water delivery system for the vegetable farms using the knowledge we've gained from SETG 2343 fluid mechanics course. The water delivery system in our project is made up for four different types of component: a sand separator hydrocyclone, two pumps, which is centrifugal pumps, a sand filter, and PVC pipes that correspond to each unit's location and join them all together. Both big and minor head losses will be impacted by the different types of pipes and pipes coupling. We had to use eDrawmax to draw the water supply system and specify the dimension of each unit after conducting our research. These measurements and drawings allows us to calculate the head pumps and the building's construction cost. So, for the introduction, as a background story, a vegetable farm is in need of water supply to supply water for its daily vegetable farm consumption. The nearest river is located 500 meters away from the vegetable farm, and the water supply also must be able to supply to all 4 acres of area of the vegetable farm. Also to note, the water supply must be clean before supplying it to the farm, as poor quality of water may lead to poorer quality of vegetables. When planning and designing this water supply, there are a few things that we have to take into consideration. One, project cost. We must keep it as low as possible. Pipe leakage. We have to avoid any pipe leakage. And third, environmentally friendly. The water supply must not be polluted environmentally. So, based on the background story of this project, we have come up with two objectives. First one is to be able to build and design a water supply for the vegetable farm by collecting any relevant information and data, gathering such as water flow rate, net positive suction head, and pump efficiency during periods of high demand. And second objective is to apply a Bernoulli's equation and fluid mechanics knowledge to discover a reasonable, simple, robust, and economical method of building pipelines, pumps, and engines. After a bunch of try and errors, we have come up with four main components. Number one is sand filter, number two is main water pump, number three is secondary water pump, number four is sand separator hydrocyclone. Main water pump will pump water from the source up until the sand separator hydrocyclone. Sand separator hydrocyclone will separate the sand that's from the river with the water that has been cleaned. After that, it will be delivered to sand filter, in which here, with bunch of layers, it's gonna help to clean up the water even more to remove any dust or particles. And lastly, secondary water pump will pump the water from sand filter up until the crops to supply water to the 4 acres of vegetable farm. Here we have the overall system. First, the water source from the river will be pumped by the main water pump to sand separator hydrocyclone. And then from sand separator hydrocyclone, it will go to sand filter. And then after sand filter, water pump will pump the water from sand filter, and eventually clean water will be supplied to the crops.
So for the methodology, step 1 is to obtain flow rate from the sand filter to pump 2. And step 2, from the flow rate we can obtain the velocity of the water. And the step 3 is to apply Bernoulli's equation to find HA that are needed for pump power. Step 4, before finding HA is calculated by obtaining the total of both major losses and minor losses of the pipe. So for the methodology, so step 5, Reynolds number is obtained to find the major losses and is obtained from Woody stack. Step 6, after obtaining major and minor losses, we can find HA. Step 7, pump power cannot be obtained after finding HA. And then step 8, after pump power is obtained, we can calculate NSD to find the maximum efficiency and the type of pump. So step 9, we can find the IPSH for pump 2. Step 1 until step 9 is repeated to find the pump 1 data, where pump 1 is from the river until the sand separator. So here is our overall planning schematic for the water delivery system to the vegetable farm. So the vegetable farm has around 4 acres of land, or close to 16,187.4 meter cube. So we assume the flow rate throughout the sand filter to pump 2 is 7,000 gallon per day for 1 acres. So we calculate from the sand filter to the vegetable farm pipe first. So we assume 7,000 gallon per day for 1 acres, and then we obtain from gallons per day we change to meter cube per second, and then we times by 4 for 4 acres, and then we obtain the value of 1.2266 times by 10 power of negative 3 meter cube per second. So like I said just now, we calculate from the back for our sand filter to our vegetable farm. Here we apply Bernoulli's equation where P1 and P2 equal 0 as for pressure atmosphere. V1 equals 0 as because sewage reservoir. Z1 equals to 0 because it is set as datum. And then Ht is equal to 0 because there are no additional mechanical device are used. Then we left with Ha equals to V2 square over 2G plus Z2 plus HL. So before finding the Reynolds number, we can find the velocity of the our velocity. So where we use Q equals to AV, when we obtain velocity equals to 0.0190 meter per second. So the next step is to find the Reynolds number at temperature 20 degrees, where Reynolds number is equal to density times by velocity times by diameter over dynamic viscosity, where the value we will get turbulent because it is greater than 4,000. So now we can find HL major, as we have found our type of flow where we use new discharge, and F is equals to 0.014, and then we obtain the HL major value. So after finding HL major, we can find HL minor. So to find HL minor, we can use KL times by velocity square over 2G. Then we obtain the HL minor, we can find HL, where is the sum of both HL major and HL minor. Next, we can find the HA, where HA equals to V2 square over 2G plus by height plus by HL. Then we obtain the value of HA. Then we can find the pump power using the formula density times by gravitational constant times by flow rate and times by HA. And we obtain the value of pump power is in watt, 36.037 watt. And then we can convert it to horsepower, which is over 746. And then we can obtain 0.0483 horsepower. And then we can calculate the NSD, where N equals times by set Q set flow rate over HA power of 3 over 4, and N is 2000 RPM, which is the average pump rotation, Then we can obtain the value we can find the type of pump, which is centrifugal pump, and the maximum efficiency is 90%. Next, we can find the NPHA equals to where is equal to pressure atmosphere over density times by gravitational constant minus height minus head losses minus vapor pressure over density times by gravitational constant, where we obtain vapor pressure at temperature 20 degrees equals to 2.338 times by 10 3 power of 3 Newton per meter cube per meter square, where and then the pressure atmosphere is 101,325 Pascal. And then we obtain the NPSHA equals to 7.1085 meter. So our HR is 7 meters, and so our NPSHA is greater than NPSHR, and then there will be no cavitation factor in pump 2. So next we will calculate pump 1, where pump 1 is from river to the sand separator. So just like now, so the difference is we assume pump 1 will gather 8,000 gallons per day because pump 1 needed more than pump 2 flow rate because pump 1 needed to supply it to the sand separator and sand filter. So then we obtain from 8,000 gallons per day, we convert it to meter cube per second, then times by 4, and we obtain the value of our flow rate, which is 1.4018 times by 10 negative 3 meter cube per second. Next will be applying the Bernoulli equation, where P1 and P2 equal to 0 because of pressure atmosphere, V1 equal to 0 because huge reservoir, and then Z1 is set as datum, and HT is 0 because there are no additional mechanical energy. So we obtain HA equals to V2 square over 2G plus by Z2 plus by HL. Then we can find the velocity using Q equals to AV, where V equals to we can equals to 0.02766 meter per second. Next. So next we can find the Reynolds number, where Reynolds number equals to density times by velocity times by diameter equal to dynamic viscosity, and then the value we obtain is greater than 4,000, which is turbulent. Then we can find HL, where HL measure where we obtain the frictional factor equals to 0.036. Then we can, after obtaining HL major, we can obtain the HL minor. Where after we obtain both HL and major and HL minor, we can obtain the HL by adding up both HL major and HL minor. Then we can calculate HA equals to, where HA equals to V2 square over 2G plus by height plus by HL. So next we can find pump power. So to find pump power, we can use the formula rho GHA, rho GQHA, and then we obtain our pump power equals to 41.2007 watt. And then we can convert it to horsepower by dividing it with 746. Then after that, we can obtain NSD equals to N times by set of Q over HA 3 power of negative power of 3 over 4. And our N is 2000 RPM, which is the average rotation of pump. Then we can obtain the NSD, where our NSD is centrifugal pump, and the max efficiency of our pump is 90%. So now we can find NPSHA equals to pressure atmosphere over pressure times by gravitational constant minus H minus head losses minus pressure vapor over uh, density times by gravitational constant. And our vapor pressure is at temperature 20 degrees, equals where it is equal to 2.338 times by 10 power of 3 Newton per meter square. So our pressure atmosphere is equals to 101,325 Pascal. And then we obtain the NPHA equals to 7.1079 meter, which is greater than NPHR, which is 7 meter. So it is greater, meaning our pump 1 will be no cavitation happen.
The calculation of electrical consumption, we total up the work of pump per month, which is 0.07723 kilowatt, multiplied with 24 hours and 30 days, and then we get the 55.6056 kilowatt per hour. And then for the commercial tariff, our project use the tariff B, which is low voltage commercial tariff. For the first, the 200 kilowatt per hour per month, we know that the current rate is 43.5 cent per kilowatt per hour. And then for the electrical consumption, we multiply with the total work pump with the 0.435, which is, and we get the 24 ringgit and 90 cent per month. For the calculation of water delivery system construction, we calculate the piping system and the component equipment. For the piping system, our diameter of the PVC pipe is 0.254 meter. For the price which is the PVC pipe per 1.45 meter is 24 ringgit and 75 cent. For the total length of pipe in our project is 500 meter, and then the total cost is 8,534 ringgit 48 cent. For the component equipment of sand separator hydrocyclone, cell filter, and 2 centrifugal pump, the total cost is 61,779 ringgit and 9 cent. For the total cost of delivery system construction, for the piping, component, electricity consumption, we get the total out is 70,335 ringgit and 57 cent. For the discussion of our project is the total of the volume of entire system is 1.4228 meter cube, which is for the sand separation hydrocyclone is 0.1728 meter cube, and then for the sand filter is 1.25 meter cube. For the total of the volumetric flow rate of our system is 2.6284 to the power of negative 3 meter cube per second, and which is for the sand separation hydrocyclone is 1.4018 to the power of negative 3 meter cube per second, and for the sand filter is 1.2266 to the power of negative 3 meter cube per second. We obtain the head pump using the Bernoulli equation, which is we get the sand separation hydrocyclone is 3.0011 meter, and for the sand filter is 3.003 meter. And then we get the total work of the water pump is 77.2377 watt or 0.1310352 horsepower. And then we get the efficiency for both centrifugal pump 1 and pump 2 are 90% and 93% respectively. And then the electrical consumption is RM24 and 90 cents per month. For the conclusion, in the period when making this project, through the use of calculation and knowledge gained from the fluid mechanic course, here our knowledge of fluid mechanic was pushed to the limit from calculating Reynolds number, head losses, pump power, NSD, and the NPSH. Also, we gain a deeper understanding of the application of fluid mechanic as we need to apply when designing and planning for our water delivery system that are used in vegetable farms. To conclude, having a deeper understanding and the knowledge for fluid mechanics can greatly enhance us to build a more efficient plant that can help us to make our life more easier and better for the generation to come. I think that's all from us. Thank you.